So in the previous discussion, we talked about various aspects of memory, RAM. Now let's do a proper estimate, okay, for DDR4 RAM. So DDR means double data rate. So there is a clock speed for the bus. So the double means we need to multiply by 2. So that's the dual data rate. Now it can transmit 64 bits per clock cycle. 64 there are 64 buses. Now I want to convert it to bytes. So I divide by 8. So that means clock speed multiplied by 2 multiplied by 8. That would be the data rate for DDR. Now if we say DDR4, then we need to multiply this number by 4, because in one clock cycle there are 4 times the data transfer with DDR4. So now let's look at the real data transfer for DDR4 RAM, which has clock speed of 400 megahertz per megahertz. Okay, so we have 400 multiplied by 2. This 2 is coming here. Then we have 8 bytes and this 4. So if you multiply all of it, you get 25600 megabytes per second, or 25.6 gigabytes per second. Okay, so that's the data transfer rate. Now compare this with the CPU data processing rate. It's in terabytes, right? Teraflops. So we are going to compare that number in this lecture a bit later. So is RAM fast enough to supply enough data to CPU? That's the question we're going to ask in a while. Now, so much about RAM. Now we can also, the RAM size is around typically 128 gigabytes, 64 gigabytes in desktops, but in laptops is 16 gigabytes. But we need to store much more data, in terabytes of data. So those data are stored in hard disk or solid state device. Okay, solid state drives. So let's look at the typical capacity of these devices, but please keep in mind that these devices are slower than RAM. So there are two types, as I said: SSD, solid state drives, and hard disks. So they are taken from Wikipedia, these solid state drives. So in solid state drives, so I'm going to just show it here. There is no, well, in hard drives we have magnetic heads. So in fact, there's a disk which is spinning. Okay, there's a disk which is spinning, and there's a magnetic head which will read while the disk is spinning. So these are not very robust because in my laptop, if I move my laptop, it's possible that this head may get disaligned and the hard disk may just crash. So, but now modern laptops come with SSD. Hard disks are not there in most of the modern laptops. Now, the data drive transfer rate is 100 to 200 megabytes per second. Okay, compared with DDR RAM, which was 25600 or 25,000. Okay, now this is much slower, and the capacity can be 20 terabytes up to 20 terabytes. SSD is faster by around 5 times, but the capacity is lower, and of course SSDs are more expensive. Okay, anyway, so this is just for information. Our programs and the data which we are running it in our computer should be there in RAM. From hard disk is transferred to RAM, and from RAM it goes to cache. So if you get data from hard disk all the time, your program will be slow. So we should make sure that data fits in RAM, CPU will work on the data, and the results are transferred finally to the hard disk. You do not want to access hard disk frequently, okay, as less as possible. Okay, now we want to talk about the connections between various devices and how fast they are. Your device will be fast, but if your connections are not fast, then you won't get performance, right? For example, I'm in a very fast car, but the roads are not very fast, or roads are a lot of potholes, then I can't move my car very fast. Okay, so we need to have pretty fast lanes or pretty fast connections. So lanes are like roads between different devices. So we can see it here. We had this kind of diagram in my discussion with the hard disk for the full computer architecture. So this is CPU, this one. Then we have North Bridge here, which will connect to RAM and GPU. So these are connection. And South Bridge, which connects with pen drives and other devices. Okay, a printer here. So there are buses. There are, in fact, bus is like roads or lanes. Now let's look at the speeds of these lanes. So PCI 1, which is old generation. So this is peripheral component interface PCI. So PCI 1, first generation X16, the 16 buses, which is 4 gigabytes per second. So PCI 2. So presently we have PCI 5 or PCI 6. So PCI 5 with 16 buses will be 63 gigabytes per second. So this is a 5th generation PCI. Now we also have 6th generation PCI, which is PCI 1 will be 64 gigabytes per second. So we are sitting here, or PCI 5 here. So we can transfer 64 gigabytes per second, okay, with this bus. And remember, our RAM could transfer up to 25 gigabytes per second. So the buses are now good for RAM, reasonably okay for RAM transfer. So the RAM, what it can transfer, can be supported by PCI. That's what I mean. Now PCI 4, data runs on the bus. So there are 4 into 16. So there are 128 lanes. Okay, so that's the calculation, and so it can transfer 31.5 gigabytes per second. The PCI 4 we had in the table, PCI 4 31.5 gigabytes. So that's the calculation. Okay, so compared with the memory transfer in DDR4, which we just discussed, is 25.6 gigabytes. So that's what I said is PCI 5 is 63 gigabytes. So this bus speeds and RAM speeds are comparable. However, we have in the NVIDIA's GPUs have much faster data rate. So it can be as fast as 600 gigabytes per second. So of course GPU can operate on much bigger data sets with faster rate. Okay, we're going to come to that later. So GPUs can work with bigger data, the faster rate, so it requires bigger data transfers. So NVLink is NVIDIA link, which is 10 times faster than PCI 5. In fact, yeah, so that's the fastest data transfer in present times. Now back to Rome processor. So let's look at the numbers. We'll look at only one column. Okay, just one column. These are Intel, 2 AMDs and 1 Intel. So let's look at the relative. It's a summary, in fact. Let's look at various data transfer rates or access times. So these are access times. We should focus on here. So L1 cache Okay, so this cache is sitting close to CPU, means the processors. So it can access, so CPU can access data in nanoseconds. Okay, so 4 cycles. 4 cycles it will require to transfer data from L1 cache to CPU. Okay, so we have 3 gigahertz, so 0.3 nanosecond multiplied by 4 will give you 1.18 nanosecond. So 3.4 gigahertz, so you can compute in terms of time, 1 by frequency is time, and multiply by 4 will give you that. Okay, now L1 cache is the fastest. I would like in 1 cycle, but well, of course not possible. So 4 cycles it can do. By the way, the data sitting in register can be operated in single cycle. So register is the fastest. Data sitting in the registers can move in the fastest way. So L1 cache is the second fastest. L2 cache takes 13 cycles in this processor. So it takes 3.86 nanoseconds. So it's 3 times slower. L3 cache is further slower by 3 times, 10 nanosecond. Now RAM is slower by factor 10, right? 10 nanosecond and 113 nanosecond. So you would like the data to be sitting in cache when I want to operate on it, and that's a challenge. But you see what's the challenge? L1 cache is only 32 kilobytes. Okay, so I can only store 4 kilo. Double precision requires 8 bytes, so I can have only 8,000 numbers. Now, of course, 8,000 numbers are too small for any realistic computations. So data keep flowing from RAM to cache, and as long as whatever I need is sitting in cache, I'm okay. But sometimes if I need something but it's not there in cache, then I need the CPU will wait, and that can cause some delays, a lot of delays. Okay, so cache usage and cache miss is called cache miss, is a big problem in a CPU or for the efficiency. Now, a memory bottleneck, let's just compare the speed of ROM processor and how fast the data can reach the ROM processor. So ROM processor has 8 channels, means there is a RAM, and there are 64 cores, and there are 8 ways data can flow into the cores. So each channel can supply at 25.6 gigabytes per second. Remember DDR4, we estimated this a few minutes back. Now the total transfer, if the data is easily available, channels are all active, there's no blockage of data anywhere. So I just multiplied 24.6 into 8, which is 204 gigabytes per second. So we have 24.6 gigafloats. So there are 8 bytes per float, right? A double, actually I should say double, giga double, okay? So real floating point number or real numbers. So 24.56 giga real numbers. So I can transfer that many numbers in 1 second, 24.6 giga. Now process 2 trillion floating point operations. We showed that from the clock speed, that's the maximum possible. So if it did all the operations very efficiently, data is available in cache, it can do this fast. 2 trillion floating point operation. It's a theoretical peak. Now see whether data can flow at that rate. You see, it can only supply, the memory can supply only data this fast. Of course, from cache it can flow faster. So if data is not there in cache, then we are not going to match this, right? I mean 2 trillion versus, so that is 2000, 2 trillion is 2000 giga, and we are only 25. So the difference is 80 times. So if the data flows from RAM only, we will be short by 80 times. But because of cache, it is faster. We can reach, well, not to the theoretical peak, but we can do better than this 80 times slow speed. So data in cache is accessed faster. So with L1 cache can send data 32 bytes or 4 words per cycle. And so if the data, whatever I need is there in cache, then I can reach 64 core, 4 words, 3 gigahertz, multiply with that. So 0.75 trillion operations can be performed in principle. So I can't get 2 trillion, but I can get 0.75 or close to a trillion operations per second. Okay, so that's the estimate. Okay. Of course, in real applications, we can't make sure that everything what we need is there in cache. But anyway, if you do it properly, optimize in a very clever ways, we can reach close to the peak. So you can look at the memory speeds and CPU speeds, etc. in your own machine. So this for my laptop. So we had this one has Apple M1 chip, 16 gigabytes of RAM. In this laptop, this normal or good RAM, and it is a 13.3 inch display. It has that many pixels, and this is the hard disk. Okay. Anyway, so you can look at your own machine. So there are some, I mean, you can just do click and find it. Okay, I don't know how to do it in Windows or Linux, but there are ways to find it very easily. Okay, there's some more information, what kind of RAM it is, DDR4, all that information is available inside those device configurations. Okay, thank you. So we stop here, and we will discuss further on, in fact, next talk will be on operating system. Thank you.